Trigonometric integrals are really integrals that are using a sneaky substitution based on trigonometric identities. We're going to start off with a straightforward substitution example and then use a similar problem to motivate exactly what we do. Here we have the integral of the cotangent to the fifth of x multiplied by the cosecant squared. And I recognize that the derivative of the cotangent to the fifth is negative cosecant squared. So I almost have exactly what I need there. I'm going to let u be equal to the cotangent of x. Then du is negative cosecant squared x dx. And I'm missing that extra factor of -1, so I'm going to pull it over to the left side, multiply both sides by -1, and we end up with negative du is cosecant squared x dx. So the cosecant squared here, we're going to replace by negative du. So negative du, and I don't need much room because the cotangent to the fifth, the cotangent is u, that becomes u to the fifth. And we just use our ordinary formula for the power. We'll have -1/6 u to the sixth plus a constant, and we resubstitute u equals the cotangent of x. So -1/6 cotangent to the sixth of x plus c. All right, compare this integral with the next one we're asked to compute. The next one has cotangent to the fourth. What we'll do is we recognized that the cotangent squared, or the cotangent's derivative was negative cosecant squared. Well, I'm going to save off the cosecant squared here, and it's kind of mysterious right now why I'm doing that. But let's save off two factors of the cosecant. Here we go, cosecant squared x. And then I'm saving off two factors of the cosecant squared of x dx because it's related to the derivative of the cotangent. All right, so what we need to do is we need to pull out some of our trigonometric facts. And I'm not really good at remembering this one, so I always kind of have to derive it on my own. My favorite trigonometric identity is probably everybody else's favorite trigonometric identity. Cosine squared of x plus sine squared of x equals 1. Now I have cotangent and cosecant. I really could focus on either of those. Let's focus on the cotangent. What is the cotangent in terms of the sine and the cosine? The cotangent is the cosine of x over the sine of x. So what I need to do is I have a sine of x in the denominator. I'm going to go through with this identity and divide everybody by the sine squared of x in order to produce the cotangent squared of x. And it produces some other things as well. Cosine squared of x over sine squared of x is cotangent squared of x. Sine squared plus sine squared is 1, and 1 over sine squared is cosecant squared of x. Okay, so I have cosecant squared in two places. I'm not going to mess with the one that's inside the parentheses, but the one that's not inside the parentheses, I'm going to replace with 1 plus the cotangent squared of x. So this becomes the integral of cotangent to the fifth of x times 1 plus cotangent squared. I reversed them, but that's okay. And then we have cosecant squared of x dx. So aside from the stuff that's paired with the dx, everything is in terms of the cotangent. And so that makes good sense to make the substitution u equals the cotangent of x. Du, just as before, is negative cosecant squared of x dx. And then we need to multiply both sides by -1. We get negative du is cosecant squared of x dx. So once again, I'll put the negative out front, negative. And then cotangent, we said was equal to u, so that's u to the fifth. 1 plus cotangent squared is going to be 1 plus u squared. And we've already started substituting cosecant squared of x dx. It was negative, which we already have, du. So we used a trig identity to replace some factors of the cosecant with the cotangent. Now we have to do a little bit of algebra. That often requires a little bit of algebra with these problems. I'm going to distribute the u to the fifth to both of those terms. We end up with u to the fifth plus u to the 7th du. And then we're going to get the opposite when I integrate of 1/6 u to the 6th plus 1/8 u to the 8th plus a constant. And we make our final substitution. It's negative 1/6 cotangent to the 6th of x plus 1/8 cotangent to the 8th of x plus a constant. So that's the general method. I like to think about it as looking at your functions that you're given, whatever trigonometric functions you have, and trying things out. Try to take one of them and think, well, what's its derivative? And let's save off factors of that derivative. See if we can write everything else in terms of the function we're differentiating. So here's a more prescribed way of looking at this. We're going to take advantage of these three trigonometric identities. Again, I am a big fan of just knowing this one and then deriving the other two like I showed you on the previous slide. Quite frankly, I don't have these memorized perfectly. I always kind of go back and think through this. So once again, identify the trig functions that are in the integrand. Often they come in pairs, sines and cosines, tangents and secants, cotangents and cosecants. So identify those. Group the derivative of one of the functions, whether it's the derivative of the cosine or the derivative of the sine, whatever it is, pair that up with dx. So in the example here, if you have secants and tangents, maybe take a secant and a tangent and replace it with the dx, because the derivative of the secant is the secant of x times the tangent of x. The key then is to write what's left, the stuff that's not paired with the dx, in terms of the function whose derivative is paired with the dx. Make the substitution, integrate, simplify first if you need to, and then resubstitute. Now, every once in a while, you'll have to use the half angle identities. Cosine squared equals half of 1 plus cosine 2x. Sine squared equals 1/2 of 1 minus cosine of 2x. The only time you have to worry about this, though, is when the cosine and sine are only each to even powers. All right, so let's look at our first one. I have the cosine to the 5th of x times the sine cubed of x. I recognize that the derivative of the cosine of 5th, or the cosine of x, is negative sine of x. So what I'm going to do is I'm going to take one factor of those three factors of the sine and just pair it up there with the dx. Don't worry about the fact that the negative is missing. So we end up with something that looks like this. Now, I recognize that this is the derivative or related to the derivative of the cosine of x. We're off by a minus sign, but that's okay. Which means that everything else should be able to be written in terms of the cosine. If not, we've got to go back to the drawing board. But I remember my favorite trig identity, cosine squared of x plus sine squared of x equals 1. And I know that the sine squared of x can be written as 1 minus the cosine squared of x. And if you find it odd that I have a favorite trigonometric identity, get one of your own, because they're really good to have. All right, so here we have the integral of cosine to the 5th of x. Sine squared we're going to write as 1 minus the cosine squared of x. And then I still have the sine of x dx here. We're ready for our substitution. The sine of x is related to the derivative of the cosine, and everything else can be replaced there. So I'm going to let u equal the cosine of x. Du is negative sine of x dx. And if I multiply both sides by -1, negative du is the sine of x dx, matching what we have there in parentheses. So I'm going to run out of room here shortly, but we're going to have the integral of, there's a negative from my substitution. So sine of x dx is negative du. Let's put that out front. Cosine to the 5th is u to the 5th. 1 minus cosine squared will be 1 minus u squared. And then sine of x dx, we have already started the substitution. It's negative du. We're going to distribute the u to the 5th through. So negative integral of u to the 5th minus u to the 7th du. we can take the antiderivative. It's going to be negative. Whoops, we don't want the integral anymore because we're evaluating the antiderivative. It's 1/6 u to the 6th, and I missed my negative, minus 1/8 u to the 8th plus c. So in this final step, I'm going to do two things. I'm going to resubstitute u as the cosine, and I'm going to distribute the negative through, which will reverse the order of that difference. So it's going to be 1/8 the cosine to the 8th of x minus 1/6 cosine to the 6th of x plus a constant. Okay, so that's how we do that first one. And I'll tell you this, if you had instead said, hey, look, the derivative of the sine is the cosine, and saved off the cosine with the dx, you could also do it. It would be a little bit more complex because you're going to have to square something squared, but it does work. Okay, so let's look at this next one. We have tangent to the 5th of 8x secant cubed of 8x. And I'm going to lead us down the wrong path to show you how you know when you've made a mistake. I'm going to say, look, the derivative of the tangent is the secant squared. So I'm going to save off the secant squared of x. Well, the secant squared of 8x, which leaves me with just one factor of the secant of 8x. All right, this is the derivative of the tangent of 8x. Well, I think we're missing a factor of 8 somewhere in there, but that's okay. So what that means is that everything that's left in the integrand, the tangent squared of 8x, that has to be written in terms of the tangent. Well, that's already done. The secant of 8x has to be written in terms of the tangent. Now I'm going to pull out the tangent formula. I know that the tangent to the 8th of, the tangent squared of 8x plus 1 is equal to the secant squared of 8x. I've got to write the secant of 8x here in terms of the tangent. How can I do that from the identity? Well, I'd have to introduce a square root, which really seems like a bad idea. It just seems kind of like we're making the problem worse by introducing the square root. So that's why this is a bad choice for this particular substitution. So let's reboot. We tried the derivative of the tangent, saving that off. Let's save off the derivative of the secant instead. I know that the derivative of the secant, and this is going to be kind of long to write, the derivative of the secant is the secant of 8x times the tangent of 8x. So I'll save off one factor of each of those. We get the tangent to the 4th of 8x, secant squared of 8x, secant of 8x, tangent of 8x, dx. Now, some people might prefer to make a substitution u equals 8x at the beginning. You're welcome to do that. I think everything will fall out pretty nicely in the end, so it's probably not necessary, but it's certainly an option. Now, we acknowledge that this is the derivative of the secant of 8x. Again, maybe we're missing a factor of 8. We are somehow. So everything else needs to be written in terms of the secant. Since this is the derivative of the secant, everybody else has to be in terms of the secant. Secant of 8x, secant squared of 8x, perfect. It's written in terms of the secant. Tangent to the 4th, not so much. So here's what we're going to do. We're going to go over here. We're going to solve this for the tangent squared of 8x. That would be secant squared of 8x minus 1. And here's the ugly thing. In order to get the tangent to the 4th, I would have to square the tangent squared. Ugh. Okay, so we're going to end up with the tangent squared of 8x squared secant squared of 8x. Secant of 8x, tangent of 8x, dx. Okay, and then tangent squared of 8x we can replace with secant squared of 8x minus 1, but that tangent squared was squared. Then we have the secant squared of 8x, and then the stuff at the end is just going to be, the same thing, secant of 8x, tangent of 8x dx. So you can see this one's not so pretty. It gets worse. So everybody inside here is the derivative of the secant of 8x related to that derivative. So I'm going to let u be the secant of 8x. And I think this is one of the more difficult derivatives to take. I remember that the derivative of the secant is the secant times the tangent, and that's kind of a sloppy way of saying it. The secant of 8x is going to be the secant of 8x. The derivative of the secant of 8x is going to be the secant of 8x times the tangent of 8x, and we have to multiply by an extra factor of 8 from the chain rule. So what students tend to forget to do is they tend to forget you have to have the secant of 8x and the tangent of 8x. They just like to write secant of x, tangent of x with the extra 8 there. Now I don't have an 8 in my problem, so I need to multiply by 1/8 on the left side. 1/8 of du is going to be the secant of 8x, tangent of 8x, dx. So we end up with 1/8. That's part of the du substitution. Secant squared of 8x minus 1 is going to become u squared minus 1, but we square that. And then secant squared of 8x is u squared. The secant of 8x, tangent of 8x, dx, we've already started the substitution. It's 1/8 du. Now, we're going to have to do some ugly simplification. I have to square out this u squared minus 1. So I get 1/8 of u squared minus, u to the 4th, I'm sorry. U squared squared is u to the 4th minus 2u squared plus 1 multiplied by u squared du. If you need to, multiply that as u squared minus 1 times u squared minus 1, and then use the distributive or FOIL property there. And now I have the extra unfortunate requirement of distributing the u squared through to all three of those terms. So I get 1/8 of u to the 6th minus 2u to the 4th plus u squared du. And we're ready to go. 1/8, the integral you can treat as a parenthesis in a sense. So we need a parenthesis there. It's going to be 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd du. Nope, no du anymore. I'm sorry, we integrated. Plus a constant, and we can make our final substitution. And just for fun, I'll go ahead and distribute the 1/8 through to make it nice and pretty. We get 1/56. U was the secant of 8x, so that's secant to the 7th of 8x. 1/8 times negative 2/5 is going to be negative 1/20, or negative 2/40, which reduces to 1/20. Secant to the 5th of x, of 8x, that is. And then plus 1/24, secant cubed of 8x plus a constant. So you see they can get kind of messy with those extra squares in there. All right, our final two examples rely upon the half angle identity. So here I have this integral of the sine squared. It's a definite integral, so I don't know if that's good or bad, but it's a definite integral. If you try to save off a derivative of the sine squared, well, the derivative of the sine, it's the cosine. There is no cosine in sight to work with. Okay, so it's kind of a confusing little problem here. So here's what we'll do. Because it's an only even power of the sine, we're going to replace this. I know that the sine squared of x is 1/2 of 1 minus the cosine of 2x. Now, some people prefer to write it like this: 1 minus the cosine of 2x divided by 2. That's fine, but then it gets kind of messy when it comes to doing the integration. So I prefer this first way. This actually does not require a substitution. I'm going to pull that 1/2 out front. 1/2 times the integral from 0 to pi over 4. And then I have 1 minus the cosine of 2x dx. All right, the antiderivative of 1 is beautiful. It's a very simple, let's be careful, we got a parenthesis there, x. Okay, now in previous videos I've given this little thing called what I call the linear arguments method. I have the cosine of 2x. 2x is a linear expression. And so because we're taking the cosine of that, we call the 2x the argument of the cosine. When I take the antiderivative of one of our standard formulas and the x has been replaced by a linear function, in order to compensate for that, we just simply multiply by the reciprocal of the derivative of the inside. This only works for linear arguments. Let me emphasize why this works. If you take the derivative of the sine of 2x, you would get the cosine of 2x, but by the chain rule, you would have to multiply by 2. We're going to divide by 2 to compensate for that. This only works for linear arguments. We want to evaluate this from 0 to pi over 4. And let's see what we get. We get 1/2. X is going to be pi over 4. Minus 1/2 of the sine of 2 times pi over 4. And then, well, let's go ahead and we'll take minus 1/2. We'll evaluate it at 0. Well, 0, yeah. And then minus 1/2 of 2, or the sine of 2 times 0. But the sine of 2 times 0 is the sine of 0, and the sine of 0 is also 0. So that second term there that I subtracted is 0. 2 times pi over 4 is pi over 2. The sine of pi over 2 is 1. So we end up with 1/2 of pi over 4 minus 1/2 of 1, which if you want to distribute, you don't have to, in my opinion, but you get pi over 8 minus 1/4. So that's how the half-angle identity comes into play. No substitution was required either, which is kind of nice. So I'm umming because I don't really want to do this last one. It's a little bit messier, but that's okay. I only have an even power of the sines and cosines. In fact, there are no cosines, so we would say it's cosine to the 0th, which is an even number, 0 is. So this I'm going to write as the sine squared of x squared. Okay? So that brings into the picture the sine squared of x, which we know from the half-angle identity can be replaced by something in terms of the cosine. Here's where it gets kind of messy. So I will get the integral. In the inside, we have to put the 1/2, and we have to put the 1 minus the cosine of 2x. And then we square that. Okay, take a quick glance and make sure I didn't make any mistakes, but the sine squared is 1/2 times 1 minus the cosine of 2x. Now, when you square a product, I have 1/2 times all this business. You have to square each factor. So if I square the 1/2, I'll get 1/4, which I'm just going to hold out front. And when I square the 1 minus the cosine of 2x, once again, we either use a formula we might know about squaring binomials, things with two terms, or you can multiply 1 minus cosine of 2x by itself and either FOIL or use the distributive property, whichever you like to call it. So we end up with 1 minus 2 cosine of 2x plus cosine squared of 2x dx. Okay, the first two, we're going to give them a green light. 1, I can find the antiderivative of. We can use the linear arguments method we discussed in the previous part, this guy, to evaluate that antiderivative. Cosine squared of 2x, we get a red light because I'm not sure how to do that. So let's do the first two and then come back to the red one. Actually, I do know how to do it, and you'll know how in just a moment. We have 1/4. The antiderivative of 1 will be x. The antiderivative of 2 cosine of 2x would be 2 times the sine of 2x, but you have to multiply by 1/2 out front to compensate for the 2 that would pop out from the chain rule. Okay, now I'm going to start all over again. That 1/4 that was out front would be distributed to 1, 2, 3 terms. It's implicitly distributed to these two terms. I've kind of factored it out. But I would need to also do it 1/4 times the integral of my red light function here. I don't know how to do this one. Oh, it's the cosine of 2x the cosine squared of 2x. cosine squared, I'm going to use the variable theta instead. Cosine squared of theta is 1/2 times 1 plus the cosine of 2 theta. I use the variable theta because I've got x in my problem, and it's not just x, it's 2x. So it's going to be a little more confusing. So first of all, let's copy down the 1/2 that's here. So the cosine squared of 2x is going to be 1/2. And then it's 1 plus the cosine of 2 times theta. Well, theta is an angle. So what angle was I taking the cosine squared of before? I was taking the cosine squared of 2x. Well, I'm supposed to replace this business by 1/2 times 1 plus the cosine of 2 theta. That means I'm going to double theta, which means 2 theta is going to be 4x. Cosine of 4x dx. Oh, okay, let me go through that reasoning one more time. Here's the way I like to think about it. Cosine squared of an angle, let me do this over here. Cosine squared of an angle is 1/2 times 1 plus the cosine of twice the angle. Cosine squared of some angle has cosine of twice the angle. My angle here is 2x. So cosine squared of the angle 2x is going to be 1/2 times 1 plus the cosine of twice the angle 2x, which will be 4x. And now we're ready to find the antiderivative. I'm going to join the 1/2 and the 1/4 together. And so we end up with 1/4 of x. Well, that will simplify just to be 1 minus the sine of 2x plus 1/8. Okay, that's those two together. The antiderivative of 1 is x, and the antiderivative of the cosine of 4x is going to be 1/4 the sine of 4x. The 1/4 once again comes from compensating for the 4 that's in front of the x there. And now I realize I left off a parenthesis over here, plus a constant. And if we distribute things, we can get some things together. So we could get 1/4 of x minus 1/4 of the sine of 2x plus 1/8 of x plus 1/4 of the sine of 4x. I'm sorry, not 1/4 of the sine of 4x, 1 over 32 times the sine of 4x. And then plus a constant. And if you really want to, we can take the 1/4 of x, which is really 2/8 of x, plus 1/8 x. We're going to get 3/8 x minus 1/4 the sine of 2x plus 1 over 32 the sine of 4x plus c. All right, for one final example, those last two inspired me. For one final example, I want to look to see what would happen if I kind of split the difference between a sine squared of x and a cosine, and a sine to the 4th of x. What if I want to do the sine cubed of x? Okay, this one is kind of different. I said if you have only even powers of the sines and cosines, you're going to use those half-angle identities. Well, I don't only have even powers. I have an odd power here. So how do we do that? Well, I would think I see a sine, I want to save off its derivative, which is the cosine. But there's no cosine in sight. But the sine is the derivative of the cosine. So we're going to do something, we're going to imagine this invisible cosine in here. And we're going to save off the derivative of the cosine. It seems really weird, but you'll see why it works. Sine squared of x times the sine of x dx. Now, there's no cosine in sight, so it seems kind of silly that I've saved off the derivative of the cosine, or a multiple of the derivative of the cosine. But sine squared of x, we saw earlier, can be written as 1 minus the cosine squared of x. And so I'm going to replace this sine squared by 1 minus the cosine squared of x. And then I have the sine of x dx at the back end, which is the derivative of cosine up to a constant multiple of -1. So I will let u be the cosine of x. Du will be negative sine of x dx. I don't have the negative in there, so I'll multiply both sides by -1. The opposite of du is the sine of x dx. It's time to substitute. Sine of x dx was negative du. and then cosine became u. So 1 minus u squared du. And now we find the antiderivative. This one is actually much simpler than the previous two. So that's going to be u, but I need the negative out front, don't forget that, minus 1/3 u cubed plus a constant. And then if I distribute the negative through and replace u's by cosines, I have the opposite of the cosine of x plus 1/3 of the cosine cubed. It's plus 1/3 because I distributed the negative through.